Okay. Oh, hi. Welcome. All right. So today we're going to talk about rates of change, ratio of change, and a slope is a ratio of change because it's change in y over the change in x. All right. All right. We got that. We didn't rehearse that. We just knew it. Let's see. So if you, I want to go to full screen. All right, so the do now we have to actually do together because it's going to hopefully tie a bunch of concepts together. And our first task is to figure out in each quadrant whether the first derivative is positive or negative. So let's look, whoops, not at that. Go back to 2. Okay. So we're going to look in the first quadrant, and we've got this graph. And remember, the first derivative is simply the slope of the tangent line. Now, if you imagine tangent lines to this curve anywhere in this first quadrant, would the slopes of those tangent lines be positive or negative? Where's our first quadrant? All right, so I'm going to draw one in. Here's one. Negative. When you look at a segment, you're trying to decide whether its slope is positive or negative, you have to read it going left to right. And if, as you look at it going left to right, your eyes are going up, its slope is positive. If it's going down as you read left to right, it's got a negative slope. And what if it's horizontal? What's its slope? 0. So positive slope, 0, negative slope. You know, if you start reading backwards, you're going to be so confused. It has to be left to right when you're looking at slope. Okay, so now, if we drew a tangent line anywhere in the first quadrant, the derivative, the slope of the tangent lines would be negative. Okay. The first quadrant, the derivative is negative. I like using the circle because it covers all the cases. Now we're going to look at the graph in the second quadrant. And again, I want to know if the derivative, the slope of the tangent line, at any point there, would be positive or negative. Positive. We see that? The slope of the tangent line, doesn't matter where you draw it, it's going to have a positive slope. So the derivative over here is positive. Okay, moving down to the third quadrant, would the derivative at any of these points here be positive or negative? Good. And what about in the fourth quadrant? Positive. Let's see if we can relate this back to the function. Look at the two quadrants where the first derivative is positive. What can you tell me about the actual function in those two quadrants where the derivative is positive? The actual graph. Here and here. What are those? When the derivative is positive, what does it mean about the graph of the function? Well, here the function's positive and over there it's negative, so it's not just negative, right? Yeah? Oh, they do happen to, in this case, the way I drew, but that's not, I could draw it somewhere else where it wasn't, and that wouldn't have to be the case. What makes it have a positive derivative? Here and here. Look at the graph in the second quadrant and the fourth. What's it? The curves are going up, okay? What's another way of saying that? What is the function doing? If it's going up, it's increasing. There you go. That's good. So the function is increasing wherever the first derivative is positive. And if I tell you I've got some graph whose derivative is positive, you know the function itself is increasing. If you know one, you know the other. Now let's look at where the first derivative is negative. What do we know about the function in both of those cases? It's decreasing. As you look left to right, you always have to read graph left to right. If the function is negative, if the derivative is negative, the function is decreasing. So here it's decreasing. Also gives you negative slopes. And over here, this is decreasing. So whenever a function is decreasing, its derivative is negative. And whenever a function is increasing, its derivative is positive. Now I want to kind of stretch this. But before I do that, I want to know if you've ever heard of the expression concave up or concave down. Oh yeah, some of you guys have heard of that? Show me with your hand like what something concave up would look like. Oh, that's actually very good. Maybe you've never heard of that, but what about something concave down? Yeah, like that. You guys can't see at home what they're doing, but all right. So yeah, if a graph is concave up, it looks like a cup. It's curved. Yeah, the curve opens up. Whenever a graph is concave up, it's curved up. And if a graph is concave down, it looks like a frown. All right. Yeah. There you go. There you go. That's how you can remember the. All right. Well, you're going to see where I'm going with this. I just had to know if you were familiar with those expressions. That was good. That was good. Now, I need you to kind of move a level down. Like we said, whenever a function is decreasing, the derivative is negative, right? Oh, before we actually get to that, I'm sorry. Let's look at where the derivative is increasing and where the derivative is increasing. Let's go quadrant by quadrant. Yeah, I don't know. I just got excited to get to the finale and I'm not ready yet. Okay, let's look at the first quadrant. The second thing, what we have to do is we got to look at, we know the first derivative here is negative in the first quadrant. And I need you guys to make up some values for me because or else it's hard to do this. Make up what the slope is right here. 0. That one's not too hard. How about over here? Just make up a number. For the slope? I don't like any of those. Negative what?
Negative 2.
All right, I like that. Negative 2. What about over here?
Negative 12.
Yeah, because it'd have to be greater than it was over here. So if you say over here it's negative 2, over. All right. Negative 12. I like negative 12. It's pretty steep, right? Give me one more. Okay. Now we're getting out of control. Now, look at those slopes going left to right. Are those slopes increasing or decreasing?
Decreasing.
Decreasing. They're going from 0 to negative 2 to negative 12. They are increasing in magnitude. That's right. That's right. But as you look at the graph left to right, the slopes, the derivative is decreasing. You see that? If you go from 0 to negative 2 to negative 12, negative 18. So the derivative is not only negative, the first derivative is decreasing. We're going to do that in each quadrant. We want to check out if the first derivative is increasing or decreasing. Get rid of that. Let's move over to the second quadrant. And we got to take a look at these slopes going left to right. Make up a slope over here that makes sense for this. I like 50. I like 50. Yeah, I was looking for a large positive number. So if you're saying a negative number, nope. All right. So what it is, it doesn't really matter. But if you're saying that that's 50, what about if I go over here?
12.
What's this obsession with 12? I don't know. Okay. And then we move over here.
9.
I heard you, Riley. I hear you. And then maybe, well, what about by the time you get up here? 0. Okay. So let's look at these slopes as we go left to right. Are those slopes increasing or decreasing? Decreasing. So the derivative, the slope, is decreasing in the second quadrant. Let me erase this so I can put that in there. So the derivative is positive, right? But it's decreasing. These slopes are positive, but they're decreasing. F prime is decreasing. All right. I'm going to go to the third quadrant. Let's make up some numbers for the slopes, and because we already know that these slopes are negative. We just want to see if these negative slopes are increasing or decreasing. So give me a slope over, you got to go left to right, so I'm going to start over here. Negative 30, right. And what about over here? Oh, I like that. Negative 16. What about over here?
Negative 9. Negative 9. Negative 9. Come on, shut her up.
Negative 4. Oh man, see, I wasn't looking. I actually thought that that was you. Sorry, I was trying to do it. Sorry. And then over here? So look at these slopes as you go left to right. Are those numbers, those slopes, increasing or decreasing?
Increasing.
They're increasing. I know they're decreasing in magnitude, but they're increasing, going from negative 30 to negative 16. So the derivative is increasing in this quadrant. We've got one more quadrant. That fourth quadrant, we said the derivative, the slopes were positive. But again, we want to see if those positive slopes are increasing or decreasing. So we'll start here to the left. Give me a number. Nope, I reject that.
Any sort of number.
Sorry, couldn't take a negative. Right? We already said they're positive over here. All right, what about over here?
9. 9.
I don't really agree with the 24, but I'm just taking it because I want to throw you a bone over there. All right. All right, but so if we're committing to 24 here, we get. All right. 59. I don't know. This one's out of. But we can't be just 9 over here. That'd be less than this slope. That'd be crazy. Crazy. All right, what would make sense over here?
6, 7, 84, 9.
I like 74. It's a good year. All right, so those positive slopes, are they increasing or decreasing as you go left to right? Increasing. So the derivative is increasing. Now is when I'm going to ask you to make the jump. I got so excited before. Just got ahead of myself. Okay. No, this is messing up over here. Okay. Now, we said that wherever a function is increasing, its derivative was positive. And whenever a function was decreasing, its derivative was negative. Now, I want to see if we could figure out the sign of the second derivative from what we've got here in each of the quadrants. Let's look at the first quadrant. If the first derivative is decreasing, just think of the first derivative as being any old function. What do we know about its derivative, the second derivative? If any function is decreasing, is its derivative positive or negative? It's negative. So whenever the first derivative is decreasing, its derivative, the second derivative, is going to be negative. In the second quadrant, the first derivative is decreasing, which means its derivative, the second derivative, is what is going to be positive or negative. If any function is going down, it's decreasing. The slopes to it, like I don't see a graph of the first derivative, but if I could graph all those slopes, you would see that they're going down, right? They're decreasing. I mean, the slope of that would be negative. I'm sorry. Remember when we had all those slopes up here, and we had the slopes started like at 50 and went to 10? If I graph those slopes, the derivative to that graph would be negative. All right, what about when the first derivative is increasing? What do we know about the second derivative? Positive. Whenever any function's increasing, its derivative will be positive. That's what you want. If any function's going up, the slopes to it are positive. And the last case, if the first derivative is increasing, what do we know about the second derivative? Positive. We're going to tile this together. I want you to actually go to the summary, and we're going to see. Oh, no, wait, don't go there yet. Sorry, I'm just really getting ahead of myself yet. Guys, in the quadrants where the second derivative is negative, is the function concave up or down? Down, you see that? So when the second derivative is negative, the function itself will be concave down. What do negative people do? Frown. So when the second derivative is negative, negative people frown, your graph is concave down. Look at the quadrants where the second derivative is positive. What kind of concavity? Concave up or down? Concave up. So when the second derivative is positive, positive people smile, right? So look, concave up looks like a cup. So the second derivative sign tells you about the concavity. When the second derivative is negative, you know your graph is going to be concave down. When it's up, your graph is going to be concave up. When it's positive, it's going to be concave up. All right, let's go to the summary. Let's put all this together. This is going to be so important this year, this connection. Don't worry, we're still going to go back and do the other stuff. Yeah, that's not so good. A little shaky. Don't make fun of my lines, kids. I was looking for a tool that was going to make them like perfect, but as long as I have something like, so look at this first case. Here's my actual graph of the function. We're going to figure out the sign of the first and second derivative for each of these cases. Remember, first derivative, it's just whether it's increasing or decreasing. First derivative sign. So do you think the first derivative for this first case is positive or negative? Positive, because it's increasing, so the slopes, the derivatives are all going to be positive. Now this is a graph of our function. Look at the concavity to see the sign of the second derivative. Do you think the second derivative is positive or negative? Negative, because it's concave down. Moving on, next little piece here. First derivative, positive or negative? Positive, because it's increasing. What about the second derivative? That's very fast, I'm surprised. Yeah, it's concave up, so the second derivative is positive. Third case, first derivative, negative. Those slopes would be negative. It's decreasing, so the first derivative is negative. What about the second derivative? Positive. And because those slopes, even though they're negative, they're increasing. So second derivative is positive. All right, last case, first derivative. And what about the second derivative? All right. So you can take apart any graph, and in every little piece, unless it's linear, it's going to look like one of these. And if you can tell the sign of the first and the second derivative just by looking at whether it's increasing or decreasing, and whether it's concave up or down. All right, so that was like the hard part today. The next part's kind of fun. I'm going backwards. I wanted to remind you about, we have two types of rates of change. We have average rate of change. The average rate of change is always going to be over an interval, and it's always between two different points. Like when you have a curve, the slope's changing, okay? But when you talk about the average rate of change or average slope, you find the slope between the first and the last point, okay? The slope is, in this case, increasing as I go left to right. But the average slope I could get by finding the slope between this point here at A and this point here at B. And so this is just the slope formula. So anytime you're asked for the average rate of change of a function over an interval, just get the y coordinates and do change of y over change of x's. Okay? So average rate of change is the normal old slope formula. You've got 2 points, you use them. But when you're asked for the instantaneous rate of change at a specific x value at one point, you're looking for the slope of the tangent line. The other one was the slope of the secant line. I forgot if I mentioned that. Between 2 points, we call it a secant line. The line at one point on a graph, that's a tangent line. And the slope of the tangent line is just the derivative. Okay? So that's the connection you got to make today. When you're asked for average rate of change, use the slope formula. When you're asked for instantaneous rate of change, just get the derivative and pop the one value into it. That gives you the slope of the tangent. I think this, the way this is labeled confused some people, but this is just saying, this is just the slope formula. If you've just labeled, what would your x coordinates be to get this for your slope formula? What do you think? X. And x plus h, right? And then your y coordinate here when at x is just f of x. Like you've seen this, right? And then here at x plus h, f of x plus h. And if you use the slope formula with these 2 points, you take difference in the y's over difference in the x's, you get that. This is the whole difference quotient. But it's just the slope formula. That's all it is. But when we wanted to find the slope at a single point, we had to get the derivative. Remember, we were very tricky when we figured that whole thing out. We had to make this distance here, h, approach 0. But all that just turned out to be the derivative. So whenever you're asked for the instantaneous rate of change, you're going to need to get the derivative and pop in that value. You don't have to use the limit definition to get the derivative. We have rules now. It's easy. Well, not easy, but... All right. And now, the last thing we're going to do today is we're going to try to see what the graph of the derivative would look like. Now, we've actually done this first one before, and I'm going to review that one, but I want to see if you guys can get some of the other ones. So here's a graph of a function, and we want to draw the graph of its derivative. Do you remember where we started when we were trying to draw? Well, like what points are obvious? Like if you're drawing the graph of the derivative, you're trying to draw a graph whose y coordinates are the slopes of that one. Max and mins, right? Wherever the slope is 0, the y coordinate on the graph of the derivative is 0. All right, we're coming up with a graph when we graph the derivative whose y coordinate is the slope of the other graph. We're graphing the slopes. So we graph the points anywhere the slope was 0. Those were going to be x-intercepts on the graph of the derivative. Then we had to look at intervals. Like we looked at, okay, well, what about up to that first 0? Are the derivatives going to be positive or negative? Positive. You see how it's increasing? The slopes will be positive. So the graph of my derivative should be above the x-axis. Right? And it starts out, you want to give me a number? Nah, it's too high for this one because I'm just looking here. I'm looking at, it looks like, because if I were to actually try to draw it here and try to figure out what it is, you know, like it's rise over run, because it kind of looks like it's up 4 over 4, doesn't it? 1, 2, so it looks like it's 1 over here, the slope. But so the slope is about 1 here, and as I go left to right, those slopes, they're positive, but what happens as I go left to right? They're decreasing until we get to 0 up here. So when I'm graphing the derivative, when I graph the slope, I'm starting up here around 1, and I don't really know exactly how it goes, but I have to go down to 0. Oh, because I said, what would the slope be right here? And I tried to like draw the line out. We could get an idea of what it is. I was trying to be more accurate than with the circle. Circle I cared about was the increasing, decreasing. Now, between this max and this min, we knew the slope here was 0 and here was 0. Are the slopes positive or negative? Negative. So where's the graph of my derivative going to be? Below the x-axis. Okay? So it's 0 here. And then as you go left to right, always important left to right, 0, a little negative. What does it look like it is right there in the middle here? It looks like -1 around, and then it goes back to 0. Oh, so 0 goes down somewhere in between the -1 and comes back. I don't know. I went too far down, but good enough. We're sketching. Come on. And then we look at the next interval. You know, between these next zeros here, do I expect the graph of my derivative to be above the x-axis or below? Above, because the slopes are positive. And again, we know it's 0 here at this min, and as we move left to right, they increase to what looks like about 1 again, and come back down to 0. So the graph of my derivative is going to increase to about 1 and come back down to 0. What about the next subinterval? Is the derivative going to be positive or negative? Negative, because the function is decreasing, so the slopes are all negative, and it's going from 0 about -1 back to 0. Does this seem a little familiar? Remember doing it? And then the last one will be positive, so it's increasing, so the slope's positive. And do you remember what we said the original graph was? What is the equation of our original function here? And the derivative, there's your cosine. So it's just a nice visual confirmation that the derivative of sine of x is cosine of x. I want you guys to try to sketch the derivative of this one. Start out where it's 0, and then try to look at each interval. Think about if it be positive or negative. Maybe imagine some numbers. Where'd it go? All right. Okay, so with this one, we started out with where the slope of the tangent would be 0. So it looks like here about a -1 and 1, right? The slope of the tangent would be 0. And then you want to look at intervals. So up to the first time it's 0, these slopes are all going to be what type of number? Positive, right? And they start out at some very large positive number, and they go down to 0. So when you're graphing the derivative, positive, it means it's going to be above the x-axis. And you start up high, a large positive value, I don't know exactly where, and come down to 0. Now, I don't know anything about these x values over here. I'm not going to even draw my graph over there. Right? So the graph of my derivative, I can only go over that far. Then we look at between these two zeros. And what kind of derivatives do we have in between? Negative. Right? So my graph of my derivative is below the x-axis. It starts out 0, more and more negative, less and less negative, back to 0. So it comes down, I don't know how far, and comes back. In the last interval, you're looking at the slopes of the graph starting down here and going right. What kind of slopes are those? Positive. They start at 0 and they're going up, 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 right? So you draw a graph, the y-coordinate is 0 here and goes up, up. Aha. Now, if you were to guess, what kind of function does this look like, the original? The original, like not the derivative. What kind of graphs go like that? Oh, I heard it. Fourth wouldn't do that because at the end behavior would be the same. Cubic, right? This function is some kind of cubic, next cube. You see how the derivative looks like a parabola? It is, because when you take the derivative of a cubic, the derivative will be some quadratic. Right? Use the power rule. So it is a fun exercise. I was going to show you one of these two. Let me just show you the very last one because that's one's going to make your mind go like, woo. Anyone have any idea what graph this is, the last one? It's an exponential graph. And when that exponent is 1, it looks like the y-coordinate is like around 2.71828. Anyone know what exponential function this is? Well, the inverse of that. That's e to the x. Now, this is cool. See how this slope is never 0? As you go left to right, the slopes start out, what kind of numbers are these slopes anyway? Positive or negative? Positive. They start out near 0. And as you go left to right, they just get larger and larger. Just like the function itself. The slopes are the same as the y-coordinates. So, like at this point, which would be 0, what? 0, 1. Guess what the slope is when y is 1? 1. Whatever the y-coordinate, that's the slope of e to the x. Isn't that the craziest function? It's crazy. The slope, the derivative of e to the x is e to the x. Yeah, that's going to be your favorite differentiation rule to remember. The derivative of e to the x is e to the x. Yeah. Now, with this homework, I have to tell you guys, I had one class that was very confused and one class that wasn't. I don't want you to think it's worse than it is. I just want to let you see this. I don't know what that said. I'm just saying yes. All right. All they're looking for in the beginning is that you know the difference between average rate of change and instantaneous rate of change. What am I saying? Oh, this one. Okay. So the first one, all they want you to do is write down what the average rate of change is going to be from x equals a to x equals a plus h. So are you going to use the slope formula or the derivative? Slope formula. So if you're going from x equals a to x equals a plus h, what are we going to write for the numerator? What would the y's be? F of n, I think it's a plus h. F of a plus h minus f of a over, it's just going to be a. That's all they want, okay? For the second one, they want the instantaneous rate of change of x at a. It's just going to be the derivative at a. You just got to write f prime of x. That's all they want. You realize it's the derivative. And then for these next couple of questions, they want you to answer either average or instantaneous. That's all you have to do is write the word average or instantaneous. You'll have to read them to see. But when you get to problem 6, you'll actually have a function, and they'll give you 2 points, and they'll say find the average rate of change. So you'll use slope formula. You'll have to get the y's. And then instantaneous rate of change, you'll have to get the derivative and plug in the value. All right, so do your best in this. Don't worry about 15 if you don't understand it, but I actually think you guys aren't going to have a problem. So have fun with this. It's actually very short, the answers. It's like one-word answers.